What's going on, everybody? Welcome to the first episode of Geologic Mapping and Structural Geology. We're just going to introduce these two books. I decided to mix them together, and I'll explain here in a few why. Okay, so I put a vote out on Asburgers Study on Facebook. Shout out to them. It's a good community if you guys want to find like-minded people that are also studying for ASBOG. You can ask questions on there and hopefully get help with whatever problem you're looking for. So obviously structural geology won the vote, but as you'll see on the next slide, geologic mapping and structural geology go together like peanut butter and jelly when it comes to the ASBOG exam, the FG or PG. You want to make sure that you understand both of those. So that's why I decided to just mix them both into one to streamline studying for you guys. And for myself too, because I have to take the PG still. But this is from the ASBOG Candidates Handbook. So in terms of general and field geology, which is mapping, you want to understand surface and subsurface exploration techniques and interpretations, geologic and geophysical tools, application and interpretation, earth processes, surface and subsurface, mapping and map applications, cross-section, photogrammetry, wow, that's a word, terrain measurement, GPS and GIS, remote sensing, image analysis and interpretation, scale and scale analysis, we'll definitely get into that, measurement theory, accuracy and precision, geostatistics, documentation and record keeping, modeling concepts, professionalism and ethics, which is more a PG thing, project planning, management, organization, economics, and then these are all split between the FG and PG. I'll let you read that on your own, but we'll basically be covering a lot of that using the Geologic Mapping book. And then from structure, tectonics, and seismology, I won't get into seismology too much, but they want you to understand fractures, faults, and folds, rock fabrics, mechanics, structural analysis, plate tectonics, tectonic regimes, volcanism, structural and seismic history, paleoseismology, and earthquake processes. And then for the PG specifically, project planning, management, organization, and economics. So that's why I decided to combine them both. They'll go together. A lot of the questions you'll face on the FG will basically combine both geologic mapping techniques to go along with structural geology. So this geologic mapping book, as you can see, you can buy it for like $10. They have a third edition out now. Well, actually it's $20, but they have a third edition out, but second edition works too. That's the one I'm using for the preparation of these slides. So we'll be going over base maps, preparation of geologic maps, identification and description of sedimentary rocks, use of aerial photographs and mapping, interpretation of superficial geologic maps, so quaternary alluvium, stuff like that, introduction to geologic maps of bedrock, geologic maps of homoclinal beds, unconformities, folds on geologic maps, faults on geologic maps, and igneous and metamorphic rocks. And I'll try to tie the folds and faults on geologic maps along with, okay, switch for me. Okay, there you go. I'll try to tie those to when we cover folds and faulting, which there's a couple chapters that go over faults, folds, and faulting. And then you have contractional and extensional regimes. We'll be going over structural analysis in this chapter today. Deformation, strain, stress, rheology, fracture and brittle deformation, kinematics and paleostress in the brittle regime, deformation at the microscopic level, foliation and cleavage, lineation, boudinage, shear zones, contractional regimes, extensional, strike-slip, transpression, and transtension, salt tectonics, which might be useful knowing, balancing and restoration, and a glimpse of a larger picture, which is basically tying everything together, I'm guessing. And I guess I should also identify so the Structural Geology second edition, Håkan Fossen is the author. So far from what I've read, it's a pretty damn good book. So maps and images used in the study of Earth. We use vertical aerial photos, which is at high altitude, and the camera is pointing vertically down. There's an advantage of showing features in their correct position relative to one another and with much less distortion than oblique photos. Ortho photographs, and that's typically what we see. So this is a vertical photograph right here, and this is an ortho. The limitations of vertical aerial photos with radial distortion are corrected in ortho photos, and it looks like a Google Earth image, basically, is what an ortho photo is. It's planimetrically correct, it's accurate, it allows for accurate measurements of area, distance, and directions, it makes better base maps, and many 1 to 24,000 quadrangles in the US are now available in orthophotos via USGS. Maps and images used in the study of the Earth. This Landsat satellite images will eventually do a whole series on remote sensing, but this gives you an idea of using remote sensing to identify the geology in an area from an aerial photo standpoint. It's pretty cool. Don't know much about it, but we'll eventually cover remote sensing. So geologic maps, wow, I can't talk today. Geologists depict their interpretations of aerial distributions of different rock bodies and superficial materials. Bodies of rocks depicted may be bedrock materials such as sedimentary strata, superficial deposits such as alluviums, volcanic extrusive like ash, and beach deposits. Also igneous intrusions and metamorphic rocks. A rock unit is a body of rock that is identified, distinguished from one another based on the composition and texture. And a formation is a basic rock unit identified by lithology and their stratigraphic position, discerning from rock units above and below stratigraphically, can be recognized and mapped at the surface and subsurface. So kind of a review of what we learned in our undergrad. And this shows a map of New York, and it's a generalized, just a generalized geologic map of New York. So Devonian, you have limestones, dolostone shells right here. Silurian, which is older, limestones, dolostone, same thing. And then the purple, Ordovician, limestone shells. And then the green, Cambrian. It doesn't say exactly what the Cambrian is. Oh, okay. Now I get it. It's a Cambrian limestone, shale, sandstone, dolostone. The yellow, that's an old rock right there, along with the marble, quartzites and marbles, and then you have anorthosite right here. Okay. And you have your north arrow, you have your scale, your latitude and longitude. So formations may be subdivided into thinner units called members. As you can see, this is the Grand Canyon. This is one formation, but these are divided into members, each one. Several formations that are related to one another are placed in larger stratigraphic subdivides called groups. So say these two are come from the same age, like Cambrian, then it would just be called a group. Although I don't know the exact geology, but I know that there's a lot of older rocks, Precambrian, Cambrian, Jurassic up here. On other geologic maps, units differ on a map called map units. They are grouped based on age, so all sedimentary rocks of Cambrian age may be grouped together. So geologic maps always contain an explanation of units on the map, and symbols explain the common symbols, which you can see on your right. Contacts between different rock bodies appear as lines. Inferred or buried contacts will be dotted or dashed. So it cut off right here, so a known fault will be a bold line. A contact between two rocks is a little bit thinner than a fault, but if it's a probable or inferred, it's dashed, and it can be dotted if it's concealed, basically. And it's good to know all these symbols, although a lot of these I've never seen before technically. It is definitely good, and typically a geologic map will come with the legend with it, so you can know exactly what you're looking at. So geologic cross-sections, which there's a chapter specifically telling you how to design a cross-section, but a cross-section shows positions of contacts between the strata or other rock bodies that you would be able to make. be able to see if we're possible to make a vertical slice of the ground. If serious distortion is to be avoided, same scales used for elevation, vertical, and horizontal distance. So this is your cross-section line right here, and then this is what it would look like when you draw it out here on the bottom right here. Structure contour maps, they depict the shape of a rock or fault surface. Okay. A shape of rock or fault surface can be depicted by the use of contours drawn to represent the surface. Such contours indicate the elevation relative to sea level of the surface of rock body in the same way topographic contours show elevation of surface of ground. Usually structure contours depict elevations of rock surfaces beneath the ground, and you'll deal with structure contours when you're doing a 3-point problem, which I have a previous video on that, but I think we'll go into that with the Geologic Mapping textbook. So the types of information provided by topographic maps. By map symbols, you'll have cultural, natural, political boundaries, latitude, longitude, scale showing horizontal distances, elevation of ground surface, magnetic declination, and the data of the map. And then what you can interpret from a topographic map is the shape of the land surface, the types of landforms, structures of bedrock, drainage basins. So from a geologic map, from the map symbols, you can you can determine topographic information, type, location of bedrock units, contacts between the units, type, location of surface deposits, type, location of faults, folds, trend or strike, and inclination, dip of rock layers. And as you can see, here's the strike and dip. It's dipping this way. This is dipping in this way. So this is probably an anticline, possibly, could be. And then you have a syncline right here, possibly. And it shows you all the different, there's no inferred contacts from what you can see on this map. They're all pretty clear contacts. And then you have a thrust fault right here, a couple thrust faults. Okay, and then what can you interpret from a geologic map? The rock structure beneath the ground surface through cross sections, the rock type of bedrock, rock hardness and consolidation, which this looks like a pretty hard area, and origin and type of material and superficial deposits. So land use maps can be derived, like you see on the left, can be derived from geologic maps: unconsolidated alluvium, human deposit fill, unconsolidated pebbles, cobbles, boulders, and clay sand, shelly soil, overlying interbedded shelled sandstone, residual soil, overlying shell and shelly limestone, marked changes in soil thicknesses, acidic, sandy soil underlain by sandstone or quartzite, landslides, karst areas with sinkholes, and based on the type of materials and slope in the area, possible to make certain inferences about suitability of the land for various uses. Areas that contain sinkholes have a high potential for groundwater contamination and the surface is unstable, and it can infer how susceptible soil is to erosion, stability of cuts, excavation, mass movement potential, important rock or mineral sources, limitations on development of the area for an urban, industrial, residential development, and suitability of land for waste disposal sites. The professional uses of geological maps: you can use them to locate rocks of particular age, lithology, or structure, construct cross-sections, reconstruction of geologic history of the area. You can explore natural resources, or you can locate water supply and groundwater recharge zones. Okay, so now we're going into the chapter 1 of the structural geology book. So structural geology is about folders. No, it's not about folders. It's about folds, faults, other deformational structures in the lithosphere, how they appear and how and why they form. They can be kilometers to microscopic details. Structures occur in many different settings and have experienced exciting changes in stress and strain. Structural geology is important for exploration, mapping, exploration of resources, ores, groundwater, and oil and gas. Geologic structures, geometric configuration of the rocks, and structural geology deals with the geometry, distribution, and formation of structures. Structures are created during rock deformation. This is a chevron fold. It's pretty. Looks like interbedded limestone and shale, maybe. I don't know. That's a pretty chevron fold right there. And it's kind of interesting. You think of solid rock, and it basically bends like it's I don't know, like it's cardboard. It's pretty incredible structural geology. So tectonics is connected with external and often regional processes that generate a characteristic set of structures in an area or region. And plate tectonics is the large-scale part of tectonics that involves movement and interaction of the lithospheric plates. Microtectonics is micro-scale deformation in structures, which obviously there's a whole chapter going over that. And this is just review. You have subduction. You have subduction on both sides, and then you have a divergent boundary right here. You have a transform boundary right here. I mean, that's plate tectonics. Eventually, I'd like to do a physical geology, going over this again, because this is one of the more interesting parts of geology, is understanding plate tectonics. So deformation, strain. Strain is something primary or pre-existing, has been geometrically modified, and there's been a change in length or shape. Being able to recognize tectonic deformation depends on our knowledge of the primary structures. Resulting deformation depends on initial materials, texture, and structure. So sandstone, clay, and limestone, and granite will produce different structures respectively because they respond differently to stresses and strains. So you have metamorphic growth of minerals, which is right here. It's called a porphyroblast. Before, during, and after deformation, which will provide information about the pressure and temperature conditions during deformation and may contain textures and structures reflecting the kinematics and deformation history. So stress, there will be no strain without a stress field that exceeds the rock's resistance against deformation. We can create stress by applying a force on a surface. And as you can see on the left, lithostatic stress is stress in all directions, all equal magnitude. If you remember from your physics, it's all equal magnitude. This occurs at depth on the Earth's surface. That's called lithostatic stress. Structural geology covers deformation in the brittle upper lithosphere as well as the ductal lower lithosphere. And as you can see, this is your lithosphere. This is the brittle part, and this will be your more ductal lower lithosphere. And then you have your asthenosphere beneath the lithosphere. So structural analysis, I copied these two. This is from a different source, as is this. Many structural processes span thousands to millions of years, and most structural data describes the final product of a long deformation history. The history itself can be only revealed through careful analysis of the data. When looking at a fold, it may not be obvious whether it be formed by layer parallel shortening, shearing, or passive bending. The same thing applies to a fault. What part of the fault formed first? Did it form by linking of individual segments, or did it grow from a single point outward? And if so, was this point in the central part of the present fault surface? It may not always be easy to answer such questions, but the approach should always be to analyze the field information and compare with experimental and or numerical models. Structural analysis generally involves three tasks: descriptive analysis, physical and geometrical description of rock structures such as the folds and faults; kinematic analysis, evaluation of the displacement and change in shape, orientation, and size that rocks undergo as a result of deformation or strain; dynamic analysis, reconstruct the forces and stresses which result rock deformation and failure, stress. Geometric analysis is included in structural analysis. It includes, which is basically what this is, kinematic. It's involved in kinematic. It includes shape, orientation, size, geometric relationship between the main or first order structure and related smaller structures, second order structures. Shape is Spatial description of open, closed surfaces such as folded layer interfaces, fault surfaces, is what it means when you're describing shape and geometrical analysis. And orientations of linear and planar structures using stereographic projection. Everyone's favorite thing to do in structural geology is using stereo nets. Brittle deformation versus ductal deformation. So here on the left shows you brittle, which means fractures occur, and ductal is basically the rock flows. It changes shape without fracturing, is basically, and this occurs deep in the crust, deeper in the lithosphere, I should say, and this occurs closer to the surface. Strain applies to ductal deformation where originally continuous structures such as bedding, like this was a bed before it was deformed, remains continuous after deformation occurs when rocks flow without fracture. Under the influence of stress, brittle deformation is when the rocks break or fracture. So thank you for watching. Let me know what you think. Subscribe if you're new. Leave a like, leave a comment. The next episode will be covering base maps and deformation from each respective book that I mentioned earlier. Thank y'all.